Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
So we're going to be considering a situation where we have a spring constant K and two masses. For this first situation, the masses are the same. Both mass values equal 3.0 kilograms. And we are asked to find the time when both of them are at the same position, x equals 0. Okay, so when an object is pulled to the distance of x equals a and then released from rest, it passes for the first time through the point where the spring is unstrained after it has gone 1/4 of the total period. That's because it gets halfway to the opposite end, which is half of the total period. So half of the total period is 1/4 of the total period. So in this situation, t naught is equal to 1/4 the total period t, where the total period t is equal to 2 pi times the square root of m over k. So, sorry about that. So m over k goes in the square root. Okay, so now if you plug in your values here, we find that this comes out to equal 0.25 seconds. For part B, we're going to change the masses. So this time, mass M1 has a value still equal to 3 kilograms, but mass M2 has a value equal to 27 kilograms. Well, if you look at the above relationship, it's clear to see that the larger mass is going to have a shorter amount of time to get to that original position. Okay, so now if we assume that one mass is released from the point the same time, so if we assume that one mass is released from the point x equals minus a to pass through x equals 0 and to return to the same initial position, you're going to add on a half amount of that original t value. So technically, the correct equation, if it's going to oscillate multiple times through, is going to be 1/4 t plus 1/2. So actually, let's write it this way. So the total value, the total time t, is going to be equal to t naught plus 2 times the number of times it's passing through that point times t naught. Well, we said that t naught was equal to 1/4 the total period, so this is 1/4 t plus 1/2 times n times t. So if n is equal to 0, meaning this is the first time it's going through, we go back to just 1/4 t. So for the faster moving mass, m2, we'll call this time t2. Assuming that it's the first time going through that position, t2 is going to be equal to 1/4 t because we're letting n equal 0. So we're going to say for this one, n is equal to 0. Okay, so plugging those values in, this comes out to be, again, t is 2 pi times the square root of m over k. So this ends up being pi over 2. Since the 2 cancels with the 4 on the bottom to give you a 1/2 times the square root of m, but this is m2 over k. Again, we're expecting this to be the shorter period because m2 is larger. So this comes out to equal 0.75 seconds. Or excuse me, the longer period because m2 is larger. So a larger mass value gives you a longer period or a longer time to get to that point. A shorter mass value is going to give you a shorter period or a shorter amount of time to get to that point. So our assumption here is by the time t2 or by the time mass 2 gets to that center point, mass 1 is already going to have passed that center point and is going to be coming back to it. So let's try it out. Let's try when n is equal to 1. For t1, if n is equal to 1, we have 1/4 times t, which is 2 pi square root of m1 over k, plus n is equal to 1, so this is 1/2 times t, which would be 2 pi square root of m1 over k. Plugging these values in, we find that this is also equal to 0.75 seconds. So after 0.75 seconds, the first mass is finally reaching that center, or excuse me, the second mass, M2, is finally reaching that center point, and the first mass, M1, is coming back to the center point after already having passed it. But they're both at that center point after an amount of time of 0.75 seconds. So that is the solution to part B.